Let me introduce Duncan from DeepBlueCapital. We'll speak about super optimizing LLVM IR.
Thank you. Yeah, so before I explain what I mean by super optimizing LLVM IR, let me just say thanks to Google for bringing me here, actually David Kipping for arranging this, and also thanks to Google because through the Google Summer of Code program they sponsored Rafael Auler's work on the super optimizer. So let me first explain what is super optimization. Since people don't mean, by optimization, people don't mean producing optimal code, they just mean producing better code. So this term super optimization was introduced to mean producing optimal code, but that's not what I'm going to mean by super optimization. So here's my own meaning for super optimization. Super optimization here is going to be automatically discovering improvements in the code, automatically discovering simplifications. I must say that wasn't my idea. John Rager had this idea of supervising LLVM IR. So my contribution was just realizing you can do a simple and limited but still effective kind of super optimization in a very efficient way. So let me just clarify that the goal here is not to have the super optimizer directly transform your program. The super optimizer is going to look at your program and discover interesting transformations. And those suggested transformations and simplifications it finds are then going to have to be checked and implemented by a human. And that means that the super optimizer can make mistakes, that's okay. If it comes up with an interesting transformation but that's actually wrong, a wrong transformation, that's okay because the human will of course spot that it's wrong and won't implement it. And of course if it spends all its time just coming up with stupid bogus transformations, it's very annoying and not very useful. But it's okay if it's got a certain number of false positives, let's say where it comes up with the transformations actually bogus. And that makes things much simpler. But before describing how Super Optimizer works, let me describe how you can actually use it. So you take your favorite program, you compile it to bitcode using one of the front ends. So for example, I compiled the entire LLVM nightly test suite to bitcode and then use this procedure. You run your favorite set of optimizers on the bitcode, maybe the entire optimization pipeline, but if you're interested in seeing if maybe early in the optimization pipeline there are some missed transformations, maybe you just run some initial set of optimizers and then use the super optimizer. Anyway, once you've got to optimize bitcode, you run a tool which is part of the super optimization suite, which extracts interesting expressions, it harvests them. So I put these 2 points together because you can do them in both together actually. And then you feed these expressions into the super optimizer, which comes up with interesting simplifications, hopefully. You then implement them, and you start again using your new improved optimizer, and you go around and around like this. Of course, the problem then is you never actually reach this profit point unless you stop one day. In practice, what usually happens, there's a few important optimizations, and then after a while, the rest is either very obscure or doesn't have much impact. And this basic approach was lifted by paper by Bansal and Aiken. So let me just show how the harvesting of expressions, harvesting of code sequences works. Uses the standard LLVM opt tool, uses a dynamic plugin pass. Here I've chosen to run all the usual optimizations and then extract interesting code sequences. So down here you've got 2 code sequences. This is on bzip2. It produces a few thousand code sequences. I've just shown first 2 here. So what is a code sequence? Well, basically, the super optimizer doesn't support every LLVM IR construct. So the harvester, it identifies a set of instructions which are all supported by the super optimizer, and it extracts a group of those that are all connected by being operands of each other. For example, if you look in the second code sequence, you can check that every instruction there, is an operand of another one or has one of the other ones as its operand. Okay, so this harvester, it just goes through the bit code, grabs these maximal collections of supported expressions and dumps them out. But actually the important thing here, the actual content, isn't these bits of LLVM IR, they're these mysterious expressions here. This is a kind of encoded form of the LLVM IR containing all the information that the super optimizers actually use. The expression is also somewhat normalized. So, for example, constants tend to be put on the right-hand side and things like this, which means that sequences which look a bit different in the LLVM IR, which are fundamentally the same, will end up giving the same encrypted encoded expression here. And in fact, all this output with LLVM IR, it's just actually for debugging purposes. It's only there because I put the details flag. The rest of the tools don't actually use it, they'll just ignore that. So typically what you do is you just don't use this flag and you just get out a few thousand lines like this. The advantage of doing this is you can actually just pipe the output straight into the super optimizer and let it analyze them. But another advantage is that you can just do textual comparisons. If you want to see how often a particular expression occurs, for example, how often does the expression 0709 here occur, you can just count how many times that particular bit of text occurs in the output. And that also means that by just using some standard tools, you can just sort these expressions by their frequency. So in bzip2, the expression 00072b occurs 265 times. This other one, 178 times. And then you can just feed this output into super optimizer in this order. So you just start by analyzing the most commonly occurring expressions. So this is, so here it's just done on one program, bzip2. I've been doing it on the entire nightly test suite, just finding the most common expressions in the nightly test suite and then seeing if they can be simplified. So just to show you some sort of notation, let me just say that obviously human beings can't work with 070A and this kind of stuff. There's a tool that pretty prints that. So for example, 070A is a sign extension operation that's extending a value to a larger type by duplicating the sign bit. Z extension, 0 extension, you add extra 0 bits on the end. Now perhaps more obscure is plus with NSW next to it. NSW means no signed wrap. That means that this is an addition operation that if it overflows as a signed addition, then the result is considered undefined. This is coming straight out of the LLVM IR, which has this concept. Basically, it's an addition where you can assume it doesn't overflow. That's what that means. So x plus minus 1, and you can assume it doesn't overflow. Greater than or equal to with an S next to it, that's a signed comparison. You take x and y as signed numbers and you're asking is x greater than or equal to y. And down here at the bottom we have power of 2. What is power of 2? That's a symbolic constant. It's, don't know what it is exactly. It might have been 8 or 16, but it's a power of 2. It's a symbolic constant. So that just gives you a taste of what these kind of things, expressions look like. So let me be more clear about what kind of expressions the super optimizer supports. It doesn't support loops. Sad, but it's a lot easier this way. So no phi nodes, no floating point, only integer operations, no side effects, so no loads and stores. And these expressions, they are type-free. There are no types. And there aren't that many constants either, only symbolic constants like sign bit or all ones value. Okay, by not having any types and not that many constants, the sort of means that these sort of expressions, at least when you don't have too many nodes, you can just, it's not unreasonable to just enumerate them, things like this. It just cuts down the number of possible expressions here. And also it means that if in the LLVM IR you have 2 expressions that only differed, for example, 2 additions, they only differed by the type, then For the super optimizer expression, it gives the same expression. So when you're ordering things by how often expressions are occurring, it will understand that those two additions were fundamentally the same thing. Anyway, within these limitations, basically every integer operation is supported. Basically, the only thing that isn't supported is byte swap, because that doesn't make much sense when you don't have any types. But bit counting, intrinsics, and so forth are all there. Okay, anyway, so once you've harvested some expressions, you can feed them into the super optimizer. This super optimizer has 4 modes. So these 4 modes, here are some examples. The first one is constant folding. For example, if you take a value x, you extend it to a larger type by adding 0 bits, then necessarily the sign bit is 0, therefore it's not a negative number. Therefore the expression a 0 extension signed is that less than 0 as a signed number? No, that's always false. So this expression actually is just a constant, the constant false. The second mode does sub-expression reduction. What that means is it looks for simplifications where some complicated expression, for example here I've got x divided by y, the s means it's a signed division, division of signed numbers, x divided by y, multiplied by y, then divided by y again, and it thinks that can be simplified to just x divided by y. Is that a correct simplification? See, the usual problem with cancelling the multiplying by y and division by y is what if the multiplication overflowed? Then it wouldn't be right. But if you first have x divided by y, then when you multiply by y, that can't possibly overflow. So then when you divide by y again, it's correct to cancel. Anyway, but the point here is that x divided by you're simplifying to x divided by y, which was already present in the original expression. It's a sub-expression of the original expression. So if I replace this division by just x divided by y, I'm definitely decreasing the amount of computation because I'm getting rid of a division and just using something that was already there, x divided by y. The third kind of transformation is detection of unused variables. For example, here you see that these two x's and x minus x plus y, they just cancel. So x plays absolutely no role here. There can be more subtle cases of this. So there's a mode which just detects that the variable x wasn't used at all. So if you think about it, that just means you could have replaced x with 0, in which case you've obtained that transformation x minus x plus y can be transformed into 0 minus y. Unlike the previous one, this does involve creating new computations. You had to create the new computation 0 minus y. Then finally, there's the fully blown, fully general super optimization, which is called rule reduction, at least that's what I'm calling it. And this was Rafael Auler's Google Summer of Code project. Basically, you have a big list of transformation rules. Super Optimizer applies these rules and tries to decrease some cost function. Smaller as the cost function means that your expression is considered simpler. So the first 3 modes are very fast. They can analyze hundreds of expressions a second. bzip2 is not that big. You can analyze all of bzip2 in just a few seconds. The last one, being a fully general super optimizer, is rather slow. So that's a bit of a problem. Constant folding, it's always a win, isn't it? Is it always a win to replace some instructions by constant? I was sure that someone would pop up at this point and say, "Oh, my architecture, you don't want to do that." So anyway, apparently not. Apparently everyone is happy that replacing things by constants is always a good thing. This reducing the sub-expression, in some sense, that should always be a win because you're always reducing the amount of computation. But unfortunately, it can increase register pressure because this x divided by y now may have to be used sort of much later on in the program than it was originally in the original computation, and that can increase register pressure. But except for that, it tends to be a win. The unused variables can also increase register pressure. Also, in this case, it might not decrease the amount of computation. You had to compute now 0 minus y, and you no longer have to compute x minus x plus y, but maybe you still have to compute x plus y because it was used somewhere else. So you may simply have just swapped one subtraction for a different subtraction. What did that win you? And didn't win you anything. So it's not necessarily a win, but it can be a win. And I have to say, this fully general super optimizer didn't actually find anything interesting yet. But it's just early days. I think with a bit more work, it will start to become useful. I'd say that these first two kinds of reductions correspond exactly to what LVM's instruction simplify analysis does. That finds simplifications that don't require creating new instructions. The other two have to go in, be implemented in LVM's instruction combine. Let me explain how constant folds are discovered. It's really ridiculously simple. Basically, you just put in lots of values and see if you always get the same result. So the first step is you assign types. There are some constraints. Comparisons, this top node, it's a sign less than comparison. So that being a comparison always has I1 type. For these register inputs, maybe you can imagine them being X and Y. You've got a choice. In this example, I'll just choose the smallest possible type. This is I1 type, is a 1-bit type, a Boolean type, in which case the other operands and the result of an add have to have the same type, so they have to be I1 as well. An extension operation is 0 extension, always is to a bigger type. If I choose the smallest possible type, that's a 2-bit type. So then the other operation, other operand has to have the same type. And there are two basic strategies for assigning types. One is just assign some random types, generally fairly small, around I8 or I4, something like this. And the other one is to choose the smallest possible types, like I just did here, or also types which are almost as small as possible. I'll say why in just a minute. Then you just put in lots of values. For example, here I chose put in 0 and 1 for these two registers. For the symbolic constant 0, of course, you put in 0, you just evaluate the expression. This sign less than comparison evaluated to 0. And again, the inputs are either chosen randomly, or if all your types are small, it actually tries every single possible value. So for example, here there are 4 possible values given these types. We'll try every one. Anyway, you keep on putting in different values. Every now and again, you change your types, put in more values, and then you see if this thing is always evaluating just the same thing, 0, and for this expression, always will evaluate to 0, in which case it just reports that it found a constant fold, that this expression is actually a constant 0. Let me explain the point of using small types. That's to catch corner cases. A lot of expressions have exceptional cases. If you get just the right value, they behave differently. For example, consider just the expression comparing x with 0. And suppose you're doing it in a 32-bit type. Then you've got 2 to the power of 32 values. All except one of them, when compared with 0, give you false. And one of them gives you true. If you just chose random values, well, almost certainly you'll never see this special value that evaluates to true when compared with 0. And so probably you'll think a comparison with 0 is actually always a constant false. But if you do it using an I1 type, then there are only 2 possible values, 0 and 1, and you will quickly notice that one of them, when compared with 0, gives true, and the other one gives false. And this happens a lot. By using very small types and looking at every single possible input, it gets rid of huge numbers of false positives. It's very effective. Here are some examples of constant folds that were found by the super optimizer. This great expression actually occurs a lot. Amazingly enough, sum 2 numbers, do a logical right shift to that by some amount, we don't know what it is, but it's a power of 2, take the result of that, and it with some other value, add a power of 2 to it, compare with 0, and the super optimizer says it's never 0. Is that true? Is it never 0? This is actually pretty typical. I mean, the super optimizer tends to come out with these very baroque expressions which have been harvested from maybe some complicated code, and you sort of have to ponder to work out what on earth is really going on here. And if you ponder this, you'll see what it's really saying is if you take a non-negative number and you add a power of 2, that's never 0. Well, actually, is that true? actually it is true, but you might have to think about it a bit. So you could ask, why is this bizarre expression on the left non-negative? Well, the whole point is the logical right shift, the power of 2 is not 0. So this logical right shift is definitely moving you right by at least 1 bit, introducing a 0, so your sign bit is 0. When you AND with something else, sign bit is still 0, so it's non-negative. Non-negative number plus the power of 2 is never 0. And this actually turns up really quite a lot. Here's another example. This question mark basically corresponds to an LLVM select instruction. So I wrote it like a C conditional expression. So if x is bigger than y, then here you get the value is x, otherwise it's y. And then this is compared with x. So what is this really all about? This is actually saying this expression is actually maximum of x and y greater than to x. Well, that's true. And these max, min idioms actually occur all over the place. I implemented a bunch of constant folds involving them detected by the super optimizer. And here are just 2 more simple examples. You divide x either with this conditional expression either by x or 1 and take the remainder. What's the remainder when you divide x by x? 0. If you divide x by 1, it's 0 too. So this is always 0. And how about this one? You take some value y, you do an unsigned division by something. Well, that definitely doesn't make the value any larger. And therefore, if you compare with itself, that's false. This is actually also quite common. But the point about these 2 examples is that what if x is 0? What if x is 0? Then in both of them, you're dividing by 0. So what do? You need to reason about undefined behavior, because in LLVM, that result dividing by 0 is undefined. So we can say when x is 0, since the result is undefined, we can take it to be whatever pleases us, and we can just take it to be 0. And the super optimizer is pretty aggressive about undefined behavior. In fact, what it does is anytime it sees something like a division by 0, something producing an undefined result, it just propagates undefined all the way up, and the result expression will be always undefined. So this is pretty aggressive, because in LLVM IR you're not allowed to do that. For example, in LLVM, if you've got an undefined value and you multiply it by 0, then the result should be 0. While here the super optimizer says undefined. Yes, multiplying by 0, it thinks that results in undefined value. The reason for doing this is because if anyone who's worked with undefined values in LLVM IR will soon have discovered there are plenty of situations where the result isn't completely undefined, it's partially defined, and so you have to give it some sort of arbitrary value. If you make an arbitrary choice and it was the wrong choice, then you can miss a simplification. So one design point of the super optimizer is that it never misses simplifications. That is to say, if an expression is constant, it will be detected. Otherwise, that's a bug. And you're sort of obliged to do this aggressive undefined behavior to make sure you never miss any possible constant folds. But it does have the danger you can get some pretty subtle false positives. It can think that simplification exists where that's not actually true, but you have to think about what happens in the undefined case. Okay, the next analysis mode was realizing that some expression, for example, x times y, but not overflowing, or if it does overflow, the value is undefined, divided by y, can be replaced with x. How do you detect this? It's basically just the same. You assign some types to everything in much the same way, assign some values, evaluate the expression, check to see if there are any nodes which have the same value as the entire expression. The expression for these inputs evaluates to 2, 2 nodes which are also equal to 2. Keep those guys. Put in some more values. Okay, I put some new values. Here, there's only now this x node down the bottom, which has the same value as the entire expression. Put in thousands, millions of additional values. And if some node, for example, this register x here, always has the same value as the full expression, then it will report that the whole expression could have just been replaced by x. Well, you'll notice here that actually what it really does is it says that this node x should have the same value as the full expression, except if the expression has an undefined value. For example, if x is 0 and y is 0, then this expression has an undefined result, while x does not have an undefined result, it's just 0. And so in that case, the value x is not the same as the value of the result, but that's okay because the result is undefined. Unused variables is much the same. Let me just explain what is the definition, really. So what I'm going to say, the variable z is unused, because if you put in any fixed values of x and y and then vary z, then the result of the expression just doesn't change as you vary z, but I will allow the result, the expression to become sometimes undefined. So for every value of z, the result of the expression is either undefined or it's some constant not depending on z, maybe depending on x and y. If you think about this example, you'll see it has exactly that property. Since z is an unused variable, for example, I could plug in z equals 0, and basically it found here the transformation that I can replace a comparison between where I do a sum of x and z and y and z. It's essential here that the sum is got undefined result. If it overflows, I could just replace that with comparison between x and y themselves. You just detect this the same way as all the others. You're just sticking in lots of values and just being careful to make sure you don't miss any corner cases. Here's some examples of unused variables. The first two are pretty straightforward. They basically just correspond to cancellations. The fact that x doesn't play any role in the first point one is basically means when you've got known sign wrap flag, you can just do mathematics like you learned at high school and just cancel out the x's. But the last two are more interesting. So the second last one, you take some value y, you do an exact right shift. An exact right shift means you don't shift any 1 bits off the end. Basically that means it's invertible. If you shift back to the original position, you get the original value. X plays, and that right shift is then going to be compared with 0. X plays no role in this, and that's actually true. If you think about it, the only way that exact right shift can be 0 is because y was 0 already. It's the same thing. And similarly with this last one, it's a left shift, but a left shift which is not overflowing. If you think of it as like multiplying by a power of 2 and it's using unsigned numbers, it's a left shift, doesn't overflow as a signed number. There too, if you think about it, indeed, you could have just replaced this comparison with the comparison y equals 0. The rule reduction is the final mode. You have to feed it a set of rules. It comes with a list of rules. It needs to be expanded, really. The rules look like, here's some example rules. Here's 0 and 1. They're not the numbers 0 and 1. They just represent some expressions. So the first rule here is saying some expression and some other expression. You could split the expressions. Commutativity. So here's a basic set of rules. You give it an expression. It computes a cost. I mean, this cost function is pretty arbitrary. Multiplications cost a lot more than shifts, for example, and that kind of stuff, as you'd imagine, but the actual numbers are sort of just made up. But anyway, so this expression actually has a cost of 22. It then applies some rules. For example, here it applies second rule. Cost went up. It actually doesn't care too much that the cost went up. It's just going to try and get the cost down in the end. It actually, of course, is applying thousands and thousands of rules. Some of these are fruitful, some of them are not. Here's a sequence which is fruitful. Applied third rule, cost come back down to 22, cost down to 11, and it can actually, and did, actually discover the so-called absorption rule, that x and y, or y is actually just the same as y. That took 1 minute. The sub-expression reduction took 0.05 seconds. Unused variables, realize that this x is playing no role. But you could also get this simplification in the same way. If x plays no role, put in x equals 0, and then you see the expression was just y, and that took 0.08 seconds. So that's kind of the problem with this, is you really need to apply this rule reduction to very interesting expressions, because it does take a while. Alternatively, you could use MapReduce and and really throw some computing power at it. Also, it needs more rules. Currently, it just has a basic set. They're not enough to find much more than some sort of reassociations. It's just a work in progress. And it's not entirely clear to me whether this approach is going to find unexpected things. I mean, are you getting out more than what you put in? What you put in is a set of rules. what you get out, you can only get out things that can be deduced from applying these rules. Can you get out unexpected things? Would it be possible to discover this simplification? That's not entirely clear, but I guess with time it should become clearer. Okay, so after having implemented a bunch of these, of course, you speed up your programs enormously. So here are some results of just implementing constant folding on some fairly well-known benchmarks. This is percentage speed up. As we all know, folding to a constant is a win. I mean, you all agreed, right? Sometimes it's a win. So this 471 Omnet PP guy sped it up by 1.5%. This 464 slowed it down by 1.5%. What's actually going on here? I can't say exactly what's going on, but I can describe in a crude form. So this 471 guy that got sped up a lot. So what happened was a lot of unconditional branches. A lot of conditional branches would turn to unconditional branches because it understood that the condition was either true or false. So thanks to that, all kinds of basic blocks became unreachable, were removed. A function was shrunk by this to the point where it was then inlined into all its call sites. And that was basically all that happened. That was everything, and that sped up by 1.5%. Now what went wrong with 464? Well, see, the thing is, what happened to 464 was actually exactly the same as what happened to 471, except there wasn't any inlining changes. Basically, a bunch of conditional branches were turned into unconditional branches, a lot of dead basic blocks were removed, jump threading kicked in, and it realized it could now jump thread some stuff, and a lot of basic blocks got permuted. There were just huge changes everywhere, but actually they all looked very reasonable. It was just basically eliminating branches, and that had a bad effect. What can I say? 400 pill bench. So the error here, I didn't know how to do error bars. The error here is supposed to be plus or minus 0.1%. I think it must be a bit bigger than that because this 400 pill bench, what terrible thing happened there? Well, the answer is 2 instructions were deleted from the final assembler. That's it. But it looks like it slowed the program down. They were deleted because they were just worked out to basically just be computing a constant. So I suspect that this 400 pill bench is just some in the noise, actually. That's my guess. And now if I put in not just constant folding, but sub-expression reduction, well, that had some good effects and some bad effects. This 483 guy got sped up now. Before it was slightly slowed down, now it's sped up by more than 3%. The reason for that's very simple. 42 multiplications and divisions were eliminated. It turns out, if I remember right, that in this program, it wants to calculate something in 100ths of a second, but actually it was actually in seconds, so it multiplies that by 100, and then later it wants it back in seconds, it divides it by 100 again, and it does sort of things like this that were all pointless, and they were just all got zapped. bzip2 got slowed down here. This is register pressure. It's clear it's register pressure. There were 25 more spills to the stack due to longer-lived variables. This is some sort of problem that I'm not sure what the right way of dealing with this was. That wasn't so good. And this guy here, one sign division got turned into a right shift. That was the only change in this program. And I guess it was a good change. Right, so I guess probably that's time up. But let me just say there are obvious improvements. One problem is that, for example, this function, which takes a 64-bit value, decomposes it into 32-bit components, recomposes them. In fact, this function actually just returns x, but the super optimizer could never find that because it's type-free. It doesn't know that you are truncating to I32. For all it knows, you're truncating to I1, in which case this series of things wouldn't just return you x again. And even more, even if you did have types, it doesn't realize that you're shifting right by 32. It thinks you're shifting right by a power of 2, and it's important that you shift right by the size of the type. it can't possibly discover this, but actually, why not work directly with LLVM IR? Well, there are several problems. The main problem is how to avoid lots of false positives. Maybe there's some tricks, not too sure. The other thing is that looking at how often expressions occur by just seeing how often they occur in the bit code, that's not how often they're executed. I mean, some expression could occur 1,000 times, each of which is executed once, and then just some guy could occur just once, but it's in the middle of a super hot loop that's executed millions of times. It's the guy in the loop that you want, but just counting how many times expressions are occurring doesn't tell you that. It just tells you how often it occurs textually. So I had an idea for this. It's maybe mad. The idea was to generate fake debug info for your bit code. So if you've got an instruction, it's part of some supported expression, like 0709. Then you write debug info saying that that instruction belongs to the function 0709. So rather than using the real function name, use this, and then you run your profiler, and it will tell you the hottest functions, but now functions are expressions, so it is giving you the list of the hottest expressions. That would be a very simple way of finding out what the most commonly executed expressions are. You can get it here. Thank you. Any questions? Is there?
You were talking about potential noise in your results. How do you run it repeatedly?
I ran it repeatedly until the standard deviation got down to the point where it was plus or minus 0.1%. Some of these benchmarks were run then thousands of times to get to that point. Yes, question over here. So the question is, could this all be done massively parallel? And the answer is certainly it can, and I've had an offer from someone at Google who's actually already using this super optimizer to do it in a big way. That might help a lot for this rule reduction, which is a bit slow for my laptop, but I guess Google can take it. Any other questions? I think that's... there's another question, maybe.
On your next slide,
Or
there's a minor reduction in improvement between 471.
Yes. it was looking good, right? Well, I had a look at it, and I couldn't work out what it was, because as far as I could see, all that happened was additional conditional branches were resolved into unconditional branches, blocks are moved around, and whoop. Now, it's, what can I say? I think it clearly needs a lot of careful analysis to work out exactly what was going on there. A question over here? So the question is this tool just finding obvious, silly things that just meant that programmer could have programmed better? I guess. Well, you could say that about almost all optimizations. A lot of things are exposed by inlining. For example, this multiplication by 100 and division by 100 over here occurred in entirely different, the multiplication and division occurred in entirely different functions. And in one of these functions, there was a preprocessor conditional. In one case, it took a value which really was in thousandths of a second and then divided it by 10. In another one, it was in seconds. It multiplied by 100 to get everything 100ths of a second. And when you actually compile it, it turned out that that was multiplying by 100 on my machine. And in some completely different function, it was being divided by 100. This is very typical for all optimizers, in fact. These kind of optimizations seem so trivial. In some sense they are, that's good. Simple, generic optimizations, constant folding, good stuff. Well, I mean, you have to start somewhere. And it's very common that all kinds of inefficiencies are exposed by inlining. When you're getting rid of a lot of abstraction layers and things like this, and you discover all kinds of little things like this. Question from Sebastian? Could I handle scalar evolution? I think I'd have to think about that. Any other question over here? So this was, the question was this with the old register allocator or the new register allocator? Yeah, this was with the new register allocator. The register pressure is a problem, not for constant folding, but so hopefully future developments in the register allocator will be more effective for rematerializing things. And I think that's the end. In any case, there don't seem to be any more questions. So.